Alright, this lesson video will take care of our first video for Unit 3. This is on counting permutations and combinations, which is part of our probability unit. Please use the notes that you received in class today to go along with the presentation. A counting problem asks how many ways some kind of event can occur. And so looking at our first example, it says how many three-letter codes are there using letters A, B, C, and D if no letter can be repeated. Anytime you're doing these kinds of problems, you want to ask yourself if the order in which items are selected or chosen matters. And in this case, since we're talking about a code, the order of the letters would matter. And so one way to solve this problem is to list all possibilities of the codes that we could have, and an organized way to do this is with a tree diagram. And so I'm going to go to the next slide to show you how to do that. This might require a separate sheet of paper because there's not a lot of space in your notes. So making a tree diagram for this particular problem might start off something like this. We have our first letter column, then we're going to choose a second and choose a third. And remember, since it's a code, we cannot repeat letters once they've been selected. So if I start off choosing an A, then my second choice can be B, C, or D. If I begin by selecting B, then my choice can be A, C, or D. And then you can see if I select C first, I can choose B, D, or A, D first, C, B, or A. And then once I select my second letter, my third letter in my code can't repeat the first two. So looking at, if I select A first and then I select B, then my third choice has to be a C or a D. In the same way, if I select A and then C, then my last choice has to be a B or a D. If I select A and then D, then my last choice has to be a C or a B. And I can do these with the remaining letters. And so I've done it again for selecting B first, B, then A, and that can be C or D. And so then I do it for the remaining two letters as well. But you get the picture, I believe. And so what you have here is 6 possible combinations for each letter, is basically what we get. We just count the end of the branches, and there's 6 in each group. So 6 times 4 would give us a total of 24 different combinations of letters for this code. Now this is one method, not a very practical method, and not a method that I would want to use for a bunch of different letters. And so we're going to talk later on about how to do this without having to go through this factor tree type diagram. Alright, this example says an experimental psychologist uses a sequence of two food rewards in an experiment regarding animal behavior. These two rewards are of 3 different varieties. And how many different sequences of rewards are there if each variety can be used only once in each sequence? So they did tell us that we can only use each variety one time in each sequence. So I have 2 possible rewards, reward 1, reward 2, and I've got 3 varieties to choose from. So, reward 1. If I start with variety 1, then variety 1, then I'm either going to get variety 2 or variety 3 for the second reward. If I start with variety 2, I'm going to get 1 or 3 for the second reward. And then if I start with variety 3, then my second reward is either going to be variety 2 or variety 1. And so counting the end of the branches, we get that there are 6 possible combinations of reward and variety. Again, time-consuming and easy to make a mistake, so we're going to talk about a way to do this without having to go through this tree diagram. Alright, the first method we have to talk about, and that one we will use quite often, is called the fundamental counting principle. And that says that suppose a certain procedure P can be broken into successive ordered stages N. And suppose that stage 1 can occur in R ways, stage 2 can occur in R2 ways, stage n can occur in Rn ways. Then the number of ways P can occur is R1 times R2 times R3. So basically, we have a successive stages. So we have different stages, so maybe stage 1, stage 2, stage 3. Stage 1 can occur in this many ways, R ways. Stage 2 can occur in R2 ways, and stage 3 can occur in R3 ways. And that, we would just multiply those together to get our number of combinations. And so now we're going to revisit example 2 using that information. Using the fundamental counting principle, the same example we just previously talked about, I have the first reward, that's my first stage, so first reward, and then my second reward is the second stage. And now, to figure out the combinations, I need to figure out how many possibilities are in each one. So for the first reward, I have 3 possibilities, three different varieties. And now for the second reward, I'm only going to have 2 different varieties, because remember, once I use one, I don't have one, I can't repeat it. So now 3 times 2, fundamental counting principle, gives us 6 possible combinations. Much easier than a tree diagram. Alright, next here we're going to mention permutations. An R permutation of a set of n elements is an ordered selection, very important, ordered selection of R elements from the set of n elements. Okay, so basically we have a set of elements, which is n, and we're going to select R elements from that set. And here, you may not be familiar with, this little exclamation mark is the factorial symbol. And in factorial, I'll give you an example of here to the side. So the factorial part is just 3 factorial, for example, would be 3 times 2 times 1. 4 factorial would be 4 times 2 times 1. 4 times 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. So you just take this number and each subsequent number and multiply those together. And that's the factorial part. And in permutations, it's important to remember that order matters. Order matters in a permutation. Okay, because that's going to determine whether we're going to use a permutation or something called a combination. So now revisiting example 1, how many 3-letter codes are there using letters A, B, C, and D if no letter can be repeated? So, note the order does matter, and we talked about that a moment ago because we decided a code, in codes, order does matter. And so we can apply the permutation formula. So I would take the permutation, I have 4 elements in the set A, B, C, and D, and I'm going to choose or select 3 elements. So again, I have 4 total elements. I'm selecting 3 of those. That's where I get my 4 and my 3, my N and my R. And now I'm going to substitute that into the formula. So that equals N factorial, so 4 factorial divided by N minus R factorial, so 4 minus 3 factorial. And so that gives me 4 factorial divided by 1 factorial, which is just 4 times 3 times 2 times 1 over 1. And so that gives me 4 times 3 is 12, 12 times 2 is 24, which is exactly what we got when we did the tree diagram. And also please note to the side that 0 factorial is equal to 1. 0 factorial is equal to 1. Alright, next we're going to talk about combinations. The formula is extremely similar to permutations. It's the same formula, in fact, except for the addition of this R factorial. And when we're trying to decide whether to use a combination or a permutation, in combinations, order does not matter. order does not matter. So looking at this example, number 3, how many committees of 3 people can be selected from 4 people? It says you can use A, B, C, and D to represent the people, or you can name them if you want to. Moses, Matthew, Mary, and Mark. It doesn't really matter. But the question I need to ask myself is, does the order matter when I'm selecting these people? So if I'm selecting a committee of people, does it matter who I choose first? And the answer to that question is no, it does not. Now, if I was selecting people and they were ranked, like a president, a vice president, and so on and so forth, then the order would matter in that case, and I would need to use a different type of situation. But since the order does not matter in this situation, we're going to be using a combination. So we're going to be plugging into our combination formula. N is 4, and R is 3, because that's the number of people I am selecting. And we're just going to substitute those values in for our N and R in our formula for a combination. So here I've substituted all those values that are necessary. And 4 factorial is 4 times 3 times 2 times 1. 3 factorial times 1 factorial will just end up as 3 times 2 times 1. And you don't have to really do any math here, because 3 divided by 3 is 1, 2 over 2 is 1, 1 divided by 1 is 1. And so I have 4 possible combinations of selecting 3 people from a group of 4 for a committee. Example 4, how many ways can the 4 call letters of a radio station be arranged if the first letter must be a W or K and no letters repeat? So again, the first question I ask myself is that does order matter in this situation? And only thing I know is that the first letter must be a W or K, and the rest of the letters, it doesn't matter what they are. And so this is neither a combination nor a permutation. It's going to be just an application of the fundamental counting principle. And so we have 4 stages, 1 for each letter in the radio call acronym. And I know that the first one has to be a W or a K. But the rest of them can be any letter that I choose out of the other letters in the alphabet. So remember, each blank I'll put in there the number of ways that can occur. So how many ways can I get a W or a K? Well, there's only two options. I'm either going to get a W or I'm going to get a K. So I have a 2, and I put that dot there because I'm going to be multiplying according to the fundamental counting principle. And now, it's also important for us to note that no letters are repeated. Okay, so now, 26 letters total in the alphabet, but now I've used one here, so I can only have 25 possibilities in the second blank. So 25. And the next one I've used 2 letters so far, one in the first blank, one in the second. Now I have 24 possibilities. And then in the third blank, I have used 3 letters now, so I only have 23 possibilities. And so now I need to multiply 2 times 25 times 24 times 23, and I get a total of 27,600 possible ways to arrange these 4 letters for a radio call station, where the first letter has to be a W or a K. This will be our last example for our video. Example 5. In how many ways can our class elect a president, vice president, and secretary if no student can hold more than one office? Alright, so first thing I need to ask myself is, does order matter in this situation? And the answer is yes, it does. Because number 1, I have rankings to my selection. I'm not just selecting and everybody's going on the same committee. And no student can hold more than one office. So once I select a student, that student can't be vice president. So order does matter in this situation. And since order matters, we will be using a permutation. So I need an N and an R. I know I'm going to be using a permutation. Now, it did not tell me the class size, so I don't know my N. And my R is 3 because I'm selecting a president, vice president, and secretary. So since it didn't give me a class size, I'm just going to set it up as we would with a number there. And instead of a number, I'll have n factorial divided by n minus 3 factorial. So there are n number of, well, I don't know, there are a certain number of permutations of 3 officers taken at a time. And so that will conclude our video. We'll take care of examples 6, 7, and 8, and 9 in class tomorrow. If you want to go ahead and try to decide on each one, if you would use a combination, a permutation, or the fundamental counting principle, that will help us get ahead for tomorrow. I'll see you then.